I've been tutoring and teaching meteorology, atmospheric science, climate, environmental science for 25 years, and I can help you gain the skills quickly. That's today on High Peak Education. So we were looking at the Convective Storm Matrix from Comet. The idea is that it allows you to input essentially two main different things, CAPE versus wind shear, but also the wind shear isn't the only thing that changes, it's the shape of the hodograph. And as I alluded to last time, as the wind rotates with height, we get more helicity. So think of helicity like a helix. So you could imagine if you ingest more helicity into a convective storm, you're more likely to produce a tornado. So generally speaking, to get the most significant supercells, we want to have high CAPE, low level moisture, drier at upper conditions. And we also want to have long wind shear. So when I mean long, I mean the length of the hodograph is long, but also the rotation of the wind direction will emphasize supercells. The most common way you can identify supercells as opposed to multicells is that a lot of times multicells come in mesoscale convective systems, so MCSs, whereas supercells tend to be more discrete, and because they're discrete and they tend to be rotating, they tend to show the rotation either on reflectivity or radial velocity or both. So one of the things we look for when we're identifying the mesoscale convective vortex is we're looking for strong, what we call gate-to-gate shear. So in terms of the radial velocity, you have a strong change in the radial velocity such that that particular cell looks like it's probably rotating. Let's have a look at high CAPE, dry conditions, and then a straight hodograph. But I'm going to assume that the 30 here probably means the amount of shear. So US here is the measure of the wind shear. So it's 0 to 6 kilometers. Part of the reason 0 to 6 kilometers is used, generally below the level of non-divergence, and generally at lower levels you've got instability. And so you also want shear where there's instability so that the cold pools will not have the rain falling into the region where the updraft is occurring. Generally, you want the updraft displaced from the downdraft to have a long-lived storm. Because if you have cold, rain, evaporated air falling into the updraft, that warm, moist updraft is going to be disrupted in terms of its temperature profile. So you want generally larger wind shear, and 0 to 6 kilometers tends to be commonly from observation. So I'm going to suggest that this is 30 kilometers for the US. We would expect if we've got high CAPE and then dry conditions and then a long hodograph, I'd say probably multicell because it's straight, not having the rotation, especially with drier conditions. Okay, so let's investigate D4. So at low levels, we've got some cold pools spreading out. They merge, kind of almost looks like two mini bow echoes to me at low levels. Do you see that? Right there and right there, at least mini bow echoes. We do have two separate bits of precipitation. They kind of split, but then we do get some refiring. So watch it right about 200 there, right there, 230 and stuff, 4 kilometers. Okay, so it kind of looks like the same story. It's just more congealed, you might say. So these are significant convective towers. And that's because we have high convection. Let's have a look at the 3D view. So pretty significant cold pool, 2 significant updrafts, a third updraft forms, and then things do spread out. If I look at from the south, the side view, looks like we've got a tall convective tower. And you see the convective tower does seem to propagate east a little bit. So watch it one more time on the south side view. So right here, this convective tower doesn't just go up, it does start to propagate, like in other words, move with the mean wind. That more so suggests multicellular over ordinary. Summary, let's see. It says linear 5 kilometers, high CAPE dry. This says weak splitting supercells evolving into a multicellular system. Whenever something starts off as a supercell, we name it supercellular. But the reason it's splitting supercells is because there's enough vertical wind shear to produce a supercell, but it turns out they don't maintain because there's not enough helicity. Watch this low-level animation again. As of right here, right there and right there, whenever they split, that's going to be indicative of supercells. But anyway, yes, it is splitting supercells that merges into multicellular convection. So believe it or not, I would recommend that we put here supercellular convection. And one thing you can say is had enough vertical wind shear to produce supercells that merged with cold pools later into multicells. So moving on, let's go for F4. Now this has a little bit of rotation to begin, but the overall shear is only 20 meters per second from 0 to 6 kilometers. I would say that's gonna probably mean multicell. But again, I'm gonna put a question mark on that because generally speaking, to get supercells, not only do you need some rotation, typically to the hodograph, you're also going to need wind shear magnitude from 0 to 6 kilometers. Now, it's typically over 25 or 30. So let's look at the simulation here. So it looks like this thing peters out pretty quick, and then it kind of pops up again and peters out. I don't see much in the way of, it's certainly not like supercell. It's either multicell or ordinary, but it's pretty piddly. So let's look at 4 kilometers. So it looks like we're just not getting much convection initiation. Too much shear, not enough moisture entrains dry air into the updrafts, and the convection initiation is not so fierce and ferocious. Okay, so with that in mind, let's look at the 3D structure. So the convection goes up, but look like it goes kind of more or less down. The cold pool spreads out, and then it initiates again over here, but not much. Weak multi-cell system. I would tend to agree with that, but at the same time, like, it's almost ordinary. The only reason I would say multi-cell here is the fact that there's more than one updraft and there is some propagation. I would say very weak, limited propagation to multicells. It turns out there's enough vertical, straight wind shear, but you're also gonna have lots of dry air entrainment. Let's look at the G's. This one's moderate cape with a rotation at the low end, straight hodograph to 7.5 kilometers, 30 meters per second of wind shear. So that's why I see here, it looks like you're getting supercells, and then G2 could be like supercell, multicell. I'm gonna suggest this one's hard to say. So let's have a look here. Now, when I look at these, this is definitely not ordinary. So if you look at these, you see how these are definitely propagating. And they tend to be pretty long-lived. So take a look at the temperature signature. Do you see that the temperature signature does seem to have some rotation in it? Mm-hmm. Do you also see they tend to split? So I'm leaning towards supercells. Also, one of the signatures of supercells as opposed to ordinary convection is that their cold pools tend to have some curvature to them and they stay out front of the supercell. Because the supercell, basically, it's got this upper level wind shear that's pushing the rain out to the front of it, but then the storm itself and the updraft is staying separated. So these cold pools, which are shown there in that yellow contour, those are kind of out front of the supercells. Let's go ahead and look at 4 kilometers. So this is, the middle of the low levels. Yeah, so again, I'm definitely leaning towards supercells, partly because also they split, okay? So a lot of times, like splitting, especially splitting, one goes more so north, one goes more so south, is more a signature of supercells. Let's look at the 3D version of this. So let's look from the top-down view first. The top-down view is going to tell us something. So we get initiation, we get the storms splitting, and then it looks to me that the clouds are rotating. The cold pools looks like they are spreading out, but then kind of trailing behind and separate. If we look at the side view, yeah, one of the things is you can kind of see those towers, they don't just propagate like multicells do, they rotate and propagate. So you think of a supercell a lot more like a top. You ever see a kid, or when you were a kid, spin a top on the floor?
Yep.
Yeah, so it rotates like this, but then it keeps going like this, right? So you think of a supercell very similar. So this says a dominant cyclonic supercell evolving into a multicell. Now evolving into a multicell, I wouldn't so much focus on that part. I would focus on the fact that it's definitely more of a supercell because they split and there's clearly a mesocyclone. That mesocyclone, again, that MVS, mesoscale vortex signature I mentioned before, you definitely see that in the rotation. So I think your analysis here of G1 under supercell, I would say I would lean this towards supercell. So it's splitting, it's got rotation, and there's enough shear and cape. The next row for the I simulation. Now I1 has even more vertical wind shear, but it's also only rotating in the low levels. Now, in this case, there's so much vertical wind shear that to some extent, more of the wind shear is dominated here than it is down here. So I would say it's very hard to say, but it might be multicell here, but it also could be supercells. So let's look at I1. So when I look at this thing, it's hard to tell what it is. So it kind of looks like a supercell, but maybe a so-called LP, low precipitation supercell. It does seem to have some rotation and propagation. So it does seem to have some rotation. If you look at the wind directions there on the 4-kilometer grid, the cold pool though is mostly near the precipitation. So I'm going to suggest that, this is probably a supercell, but this supercell is not going to be like nearly so ferocious. It probably won't produce a tornado. So here's the deal. It's got two things slightly working against it. It's got basically too much shear. So take a look. This is actually good. Look at the south view. Look at this. You see that the updraft is a lot like this. You see that? It's not very vertical. Yeah. You see how it's leaning over? That's because there's so much vertical wind shear. It's tilting the storm over. So it's not a very vertically erect updraft. And the reason it's not vertically erect updraft is because we don't have that much cape as well. So the two things that work against this storm would be not enough cape and then too much vertical shear, too much entrainment. Now it does have sufficient moisture and it does have a little bit of helicity. So it is still, I believe, a supercell. And let's look at what they said to the summary. Shallow cyclonic right moving supercell. Yeah, so I would still call this a supercell, but I'd also say that weak, not tall, lots of entrainment. Of course, it's weak cape, not a vertical updraft. Then we got to do J1. The J row has 60 for the vertical wind shear, but it looks like we're going to rotate counterclockwise as opposed to clockwise with the Hodograph. So I'd say maybe multicell, but it's hard to say. So look at that. This is an interesting situation. You see this supercell? It's actually rotating. This is like the left mover. So this time the left mover is slightly favored. Now let's explain why slightly. It's probably because we have the Coriolis force is working against the left mover, but the wind shear is such that it does favor the left mover. Yeah, it looks like a left moving supercell to me. You can see it kind of moves north and east. So yeah, look at that bad boy. See how it's rotating, but it's also rotating. It's going to start moving north. So you definitely see it spinning there. It's definitely a supercell. Shallow, anticyclonic, left-moving supercell. So shallow, because not a lot of cape, but it is a left mover because the rotation of the Hodograph is the opposite. So let's make this a supercell, but this one's unique. It's a left-moving supercell, weak due to lacking cape, not a very tall updraft. Okay.